All right, guys, we'll start now. Very good evening to all of you. Today, we're going to start with solving these actual spectra, which I have collected from a ebook called as Organic Structure from Spectra by D.L. Field and S. Sternhell and J.R. Kalman. So I got the soft copy of that book. Most of the examiner in the examinations, final examination in MSc Part 2, prefer to give the spectra from this book only. We have some other collection too. So another different forms of the spectra also we will discuss in the next lecture. But let's see some simple spectra, how to read the spectra first, and then how to come to the conclusion that this spectra belongs to so and so organic structure. Now, if you see, in the last three lectures, we have discussed about, in last three lectures, we have discussed about the different spectroscopy technique, including UV, visible spectroscopy, IR, NMR, and mass. The NMR spectroscopy include PMR, that is proton magnetic resonance, as well as C13 NMR spectroscopy. So if you see here, most of the spectra, given spectra in the examinations will be out of these three only. Three in the sense, four spectroscopy, that UV, IR, NMR, and mass. So the NMR is split into the PMR and CMR. So all the spectra which will be given to you, you have to comment on each technique and what informations have been given from that particular spectra. You have to narrate it in the form of some values, that so and so spectra belongs to so and so values. So that is the first half an hour given to all the students to read out the spectra, write down the values belongs to each spectrum, including IR, UV, NMR, and mass. So if you suppose miss out, like any spectra given, like the UV spectrum is transparent to the so and so value, and you did not comment on that, that means you understand your 5 marks will be deducted from that. So that doesn't mean that there is no any informative values. If it is a transparent to some certain functional group or certain group, that means there are certain groups which are not responding actively, but till you have to comment that there may be the sigma to sigma star or pi to pi star transition present, because any organic molecule must have some bonds, and that bonds do show some transitions, and that type of comments you have to mention. So you need not to keep it blank. So that is the informations. Now, most of the spectrum will have already given the values, like take the example of IR spectrum over here at the top. The values will be given over here. So if the values are given, no issue for finding out the functional group. But in some cases, the values may not be quoted. So you have to write down that value. Like take the example of alkyl stretch. Most of the alkyl stretch, as I told you in the lecture, that will fall below 3000. So that may be 2970, 2960, 2950. So that values you can see here in the spectrum. I can just expand this is a little bit to have clear visibility. So if you see here, the IR spectrum, this IR spectrum will have this prominent peak, that 1718. So that means there is only one value. It's not like the only one value. There are the values around 3000. There are some values around like 1200. So you have to comment each of the value. Now, how to solve, how to read out these spectra? Now, you know that.
Sir, have you changed the slide? Because your first slide is only visible yet. Workshop
Okay.
on.
Okay. Let me just share it in a different way. Just a minute. Okay. Now, is it okay? Is the spectrum
Yes, sir. Yes, sir.
visible?
Yes.
Okay.
Yes.
Okay. Now, look, in the examination particularly, this particular spectrum, I will just make it minimized a little bit because I excluded it. So this is the spectrum look like, including the UV, IR, mass, and NMR2 spectrum, like C39, proton NMR. I mean, in the examination particularly, you have to comment on each of the spectrum, and you have to write down the values belongs to that particular spectrum. Like take the example, I'll just a little bit expand this. Take the example here, IR spectrum. Here in the IR spectrum, only one value is visible, that is 1718. But there are some values around 3000. So it is told that the aliphatic carbon hydrogen stage, aliphatic carbon hydrogen stage will be around in the sense below 3000, and aromatic CH stage will be above 3000. So these two values will be easily can be given to you, that this compound may not possess the aromatic ring because there is a the molecular formula is C4H8O. So this is aliphatic structure. Obviously, the first thing you need to find out the degree of unsaturation, how many double bonds are present in this molecule. So how you will find out the degree of unsaturation? It's very simple formula, as I told you in the first lecture. So add one in the carbon and take the half of the hydrogen, and the ratio, the difference of that is the degree of unsaturation if there is no nitrogen or halogen present. So if you see here in this structure, like C4, that means 5 minus half of the hydrogen will be 4. So there will be a difference, 5 minus 4, that will be 1. So 1 degree of unsaturation, that means one double bond is present in this molecule. That molecular formula includes 1 degree of unsaturation. So this is the first information you have to draw. Then once you got the idea that there is a presence of carbonyl group 1718, so you can easily come to the conclusion that while writing the information about the UV spectrum, that you know that there is a double bond present, and that double bond is in between the carbon and oxygen. That is a carbonyl group. So obviously, this particular absorbance or OD given in this UV spectrum will be belongs to the pi to pi star and n to pi star transitions. Now, so you are going to comment in the UV spectrum that there is a possibility to have pi to pi star transition and n to pi star transition, and you have to write down the approximate values. Now the values you can see here, this lambda max is around in between the 250 to 300. That means roughly it will be 270. Okay, so this 270 or 75 is the transition, or this particular UV band is belongs to n to pi star transitions. And there is a no doubt pi to pi star transition because there is a double bond, but that will be around 200 or below 200. So prominent peak has been shown here in the UV spectrum. So another informative things you have to take it out, that is whether there is any degree of unsaturation or extended conjugations, and that extended conjugation can be drawn from this information. That is, you know, the UV spectroscopy is purely study to get the concentration of the sample, particularly the biological sample. Now, mostly we do study by UV spectrum, but in case of organic compound, like in calorimetry, we did the experiment to get the concentration of the unknown sample, and quantitative measures we used to do in the practicals. But in fact, in case of the organic structural elucidations, what informations you will get, that if the concentration of the sample is given, the length of the cuvette is given, and you know the absorbance here. From the absorbance, it is very much clear, it is around 0.7, and then the concentration will be 3.33, because I told you yesterday how to calculate the concentration. 33.3 milligram in 10 ml. That means if you just multiply by 33.3 into 1000 and 10 into 1000, if you take the ratio, that will be 3.33. That is the concentration of the sample. So if you want to calculate the epsilon over here, the molecular weight will be taken from the M plus value from the mass spectrum. So the M plus, that is the molecular weight of that compound. So 72 into OD, that is optical density, that is the absorbance, will be 0.7 upon there is a what we can say, the concentration, that is 3.33 into the path length, that is 1. So if you take this ratio, that number will be some number, integer number, maybe in thousand, or it may be the less than 1,000. If the number is in 1,000, that means that compound contained extended conjugation. If not, if the number is 10, 15, 100 up to, or maybe 1,000, like 1,000 or 1,500, that does not mean there is a extended conjugation. So if you calculate that, you can easily get the epsilon value, and you can easily comment on whether this compound having any extended conjugation or not. So this is the information from the UV spectrum. So you can comment on IR spectrum that there is a carbonyl stretching frequency in 17-18 centimeter inverse, and there is a 2970 or 2980 centimeter inverse for the carbon hydrogen stretch. And the rest of the value is not that prominent over here. So come to the NMR value. So if you see here NMR, you can see here integral value. So this integral value is related to the number of proton present in this molecule. Now there are 3 peaks. Now these 3 peaks belongs to one is a triplet and another one is quartet. Now the triplet quartet, if it is present in the molecule, that confirms that this molecule must possess the ethyl group. Because of the CH2, you will have a quartet. For the CH3, you will have a triplet. That triplet quartet pattern confirms the presence of ethyl group. So the ethyl group may be the present in this molecule. There is a carbonyl group, as we have confirmed, 17, 18. So there is a one singlet. That singlet means this may be nearby the quaternary carbon. That's why there is no any splitting. But if you see the height in the examinations, you have to carry the roller, and with the roller, you can calculate the height of this particular peak. So if I'll just highlight over here. Now you know this is a height. Now this height you can calculate it by means of a roller. You can measure. Suppose I would say this is 15 millimeter and this is 15 millimeter. So this will be, obviously this is less than this height, so that then this will be 10 millimeter. So this 10 millimeter, 15 millimeter, 15 millimeter. If you add together 15 plus 15, this will be roughly 30 plus 10, 40. 40 is the total millimeter height of the integral height of the proton NMR peak. So how many protons are there present in the molecule? If you see here, there are CH8. So 40, that means if you divide by 40 divided by 8, so roughly 5 millimeter is equal to one proton. So 5 millimeter is equal to 1 proton. That means 15 is equal to 3 proton, 15 is equal to 3 proton, and 10 is equal to 2 proton. So you can easily get the idea. This peak belongs to 2 proton, this peak belongs to 3 proton, this peak belongs to the again 3 proton. So obviously this should be the CH2 molecule, this should be a CH3 molecule, this should be a CH3 again, because from the integral height you can easily come to know the number of protons. And you know that if there are 3 protons, obviously that belongs to the carbon, and that should be the CH3. So from this PMR, you get the idea about the structural unit, that there are 2 CH3s and 1 CH2 present in the molecule. Now if you go to the C13 NMR, C13 NMR will give the 4 carbon peaks. So there are 4, if you see the carbon molecular formula, there are 4 carbons. So 4 carbon quantitatively shown here in the C13 NMR. So this C13 NMR will give you 3 peaks, but this does not couple with any DPT, but here there is a proton coupled spectrum is given. So the proton coupled spectrum gives the informations what that CH3 gives the quartet. That means the first peak, that C13 peak belongs to CH3. Second one is also belongs to CH3, and third one belongs to the CH2. And the last peak belongs to the quaternary carbon. That should be the carbonyl carbon, because the del value for the C13 is above 200. So it is confirmed from the PMR as well as CMR. There are 3 carbons, 2 with the CH3, 1 with the CH2, one other one is the carbonyl carbon. So the structural unit present in this molecule will be. So I will just use my paint. Is the paint visible? Just give me a response. Anyone? Is the paint visible? Guys, is the paint visible?
Yes, sir.
Okay. So just a minute, I will just use here pen now. Now, what structural units we got here? We got here CH3, we got here CH2, we got here CH3 again, and we have here carbonyl group. Now, if you see here, the structural unit present in these molecules are this. And from the PMR, we come to know that this CH3 and CH2 is belongs together because there is a triplet and quartet pattern. So if there is a presence of CH3, CH2 group, the left is what? This group and this two group. So the possibility to have is only this carbonyl group should be in the middle and this CH3 will be this. So the probable structure and the correct structure will be this one. But still, we have a doubt whether this structure is correct or not. So we have a mass spectrum. If you just calculate that, the ethyl methyl ketone, if you see the M plus that belongs to 72 mass unit, that is M by Z will be 72. Now from the structure that there is a fragmentation, that fragmentation belongs to 57, 43 and 29. You know that 29 belongs to ethyl group, 43 is like acylium group, and 57 is acylium with the ethyl group. So these three is absolutely matches with the structure. Now, if you see here, this particular structure, just I will draw here. Give me a minute. I have to do the job of muting you people, because when you join, you keep unmute yourself and it is a disturbance. Anyway, now this is a molecular ion peak. This is belongs to, this 57 belongs to CH3, CH2 and C double bond O. This fragment is ethyl acylium, and this 43 is belongs to acylium, that is CH3, C double bond O positive charge, and this is ethyl group, that is CH3, CH2. So from the mass spectrum, it is very much confirmed that this structure is ethyl methyl ketone. So how to just assemble the data? First, you have to get the crude data from the spectrum, that comment on this UV spectrum, then IR, and then PMR, CMR, and then mass. And then the examiner will give the time to solve, give the correct structure. And then what you have to do, once you got the structure, suppose you got this structure, then you have to comment on each value that this proton, this particular proton having, that is we call as justification. So this will have certain value, del value, that is 1 point something. This one will have something 2 point something value, and this will also have del 2 point something value. So these values you have to write with their splitting pattern. This will be singlet, this will be quartet, this will be a triplet. This, the whole process is called as justification of the structure. Whatever structures you are taken out, this structure is correct or not. Now, if you see, this is one way, that is a justification. Another one is through mass spectrum. In the last, you have to draw the structure, and then you have to do the fragmentation, and that fragmentations will be just irradiate this one with the 10 or 15 electron volt energy, and then you will get the molecular ion peak. That molecular ion peak, this molecular ion peak, maybe the positive and dot over here. Okay. And then this will be M plus, that is 72. So this M plus will be 72. Now, if you do the fragmentation, so this fragment, first fragment, this one, that is 43. This is possible to this side also. If I fragment here, this whole number will be 57. This will be 57. And then this ethyl group may go out, and that will be 29. So this way, there is a possibility to have this 29 peak, 57 peak, that 43 peak, as well as 15 also, 15 M by Z. So all these are the peak possible.
They can't see paint.
You can't see the pen?
No, sir.
Okay, somebody said me you can see. Just a minute, I will just share the screen properly.
Yes, sir. Thank you, sir.
I will completely share it. So share screen. Okay. Okay, now it is visible.
Yes, sir. Yes, sir.
Okay. So what I said, if you have ethyl methyl ketone, this ethyl methyl ketone, the overall structure will have 72 M plus value. And this will undergo fragmentation by like 43 for this acetyl group. Then this another acyl group will be with the 57. Then ethyl group will be 29. And then this methyl group will be 15. So this way, the fragmentations will be exactly matching to the mass spectrum which is provided to you, and that makes this structure is correct with the whatever data is provided in the IR, UV, NMR spectrum. So this way you have to solve the spectrum. So let me just get back to again the spectrum. Okay, so we'll go to the next spectrum. Now look at here. Hopefully this should be visible to you, spectrum. Anybody can comment. Okay.
Yes, sir.
So this is second spectrum now. We will be a little bit quick to discuss about this. And then at the end, I will give you what exactly you have to write down. Okay, this is done. No. Second one. Look here. This is a spectrum, second number. What it says, there is a UV spectrum. Now, most of the cases, when we go as an examiner, we found most of the students, they do the silly mistake that, okay, UV spectrum does not have any value. It is transparent, no significant value, means no comment on that spectrum. And straight away, you will lose a 50 marks, 5 marks over there. So never ever do like that. On every spectrum, you need to comment. You have to write some value, because there is a value given that about 220, there is a no any significant value. Means below that, there are some values. There may be the pi bond, that pi bond. If you come to know the degree of unsaturation, you can easily comment on the whether the pi bond is there or not. Suppose take this, the molecular formula C3H6O2. If you see the value, if you just get the degree of unsaturation, that is 4 minus 3, there will be 1 degree of unsaturation. That means there is a pi bond. If there is a pi bond, obviously this molecule should have pi to pi star transition. And as there is oxygen, obviously this oxygen may be the carbonyl group. So there is a 1750, so carbonyl group is there. So that means there is an N to pi star transition also present. That means in this molecule, there are the transitions possible. So you have to comment that there is a pi to pi star, maybe below 200, and above 200 will be the N to pi star transition. So these are the values for the particularly UV spectrum. You have to comment and mention though no significant extended conjugation, because there is no epsilon value provided over here. So these are the comments for the UV spectrum. Now come to the IR spectrum. IR spectrum will provide it here carbonyl stretching frequency, which is mentioned over here. And there is a very big band, or we can say the peak observed here for this. This is a very big peak, and which is mentioned over here, 3500 to 2500. That means this is a unique peak for a carboxylate OH. You know, the carboxylic acid having a OH group. So there is a OH peak, but this OH peak is with the carboxylic acid. So this confirms there is a presence of carboxylic acid group. So that also supported that there is a carbonyl group. So this value is OH stretch of what? Carboxylic acid, which is always in the dimer form. Always the carboxylic acids are in the dimer form. That's why their peak is very broad in the sense it starts with the 2500 and end with 300, 3000, or sometime 32 or 35. So this is a huge peak, and that is exactly the identity of that spectrum that belongs to the OH of carboxylic acid. So from this spectrum, you got some of the idea. Then go back to the NMR. What NMR value says. In a minute, I will show you the NMR spectrum over here. Now look here, there is again a triplet and quartet pattern. As I told you in the earlier case also, you have to carry the roller and measure this height of the peak. So this height of the peak, you can see this is related to some higher distance, and this is lower distance. Now, if you see here, suppose I would say this is 15 millimeter, so this should be 10 millimeter. So then this would be 10 and this should be 5. Okay. So if you add together, there will be 30 and there are 6 proton. Okay. So 30, sorry, this will be 30, 6 proton. So so this will be 5 millimeter again for each proton. So this will be CH3, that is 3 proton, CH2, and this will be OH because it is exchanged with D2 and this value is 11 point something. That means this is a carboxylic acid OH, that is OH proton. So the H plus is exchanged with the D2 and that becomes a tool for the identification of the active proton. So D2 exchange is normally applicable for the carboxylic acid, alcohols, amino groups where the active protons are present. And that active protons, when reacts with, this is that operational things in while taking the NMR spectrum, that whenever we are confused with the active proton, because active protons are mutuous and they always exchange with the impurity, and to locate their position in the spectrum is very difficult. So there is a operation that in the same NMR tube, we have to drop 2 or 3 drops of D2O, heavy water, and we have to shake it. While shaking, what happens? The active protons, they exchange with the impurity of deuterium, and that H will go with the D. And we know that the proton NMR have the limitation. What limitation have? The proton should have a half integral spin. And you know that deuterium will have a integral spin 1. And that will not be IR active, NMR active. So if the deuterium is not NMR active, that means it will not show a peak in this NMR spectrum. If the peak is not observed in the NMR spectrum, we have the earlier spectrum where we are very much doubtful about the OH peak, where it is lying. But we are confused. So when we compare the spectrum with the D2O, the D2O peak will be missing from that, and the which peak is missing, when we match it, you can easily locate the position of the active proton, that maybe the OH or maybe the OH of the carboxylic acid or NH2. So this is the use of D2O exchange. Now, if you see here, this belongs to CH3, CH2, and this is a OH. So if you see here in the C13 NMR, there are 1, 2, 3 peaks. This particular peak belongs to the carboxylic, that is a quaternary carbon, which is having a higher value up to something like 180, 175 something, 180, 85. That is a carbonyl peak of the carboxylic acid. Now there is a CH2 group present over here. So this carbon belongs to CH2 because it is a negative peak, and this belongs to CH3 because it's a positive. So from this spectrum, we get very clear data that there is a presence of CH3 group. This is your CH3. This is your CH2, and this is your OH. That means carboxylic acid. So from the structure, you get the idea about there is a presence of CH3, CH2, and carboxylate group. So that may be the propionic acid present from this structure. So you can easily get the idea about the structure of the molecule. Now, how to confirm that? Again, we have to go to the mass spectrum, and the mass spectrum will give the correct idea about what structure we have drawn here, it's correct or not. Now, if you see the molecular ion peak, the propionic acid will have the M plus value 74 and 57, that you know CH3, CH2, C double bond O, that belongs to 57. And there is a 45 peak, that is a carboxylic, that is C double bond OH peak, that is 45. So from this spectrum, we confirm the structure is propionic acid. So that way you have to comment, you have to justify the structure and then draw the mass fragmentation to make that structure is matching to the data which is given. So move to the next structure, that is a spectrum 3. Now the spectrum 3 belongs to now I will a little bit quicker because similar type of spectrum will be there. So if you see here from the spectrum, you will get the data about the epsilon value. You can calculate by taking this concentration and path length and this optical density. You can easily calculate the whether this molecule possesses any epsilon, that is the extended conjugation or not. First of all, calculate the degree of unsaturation. So 4 means 5, take the half of this hydrogen number, that will be 4. 5 minus 4, that means 1 degree of unsaturation is present. That means there is a presence of double bond, olefinic double bond. Maybe it is a carbonyl, because you just check the IR stretching frequency, and there is 1741. 1741 stretching frequency belongs to aldehydes or maybe the ester. If there are two OH group present and there is a carbon oxygen stretch given, that means the ester is confirmed. So from this molecular formula and the stretching frequencies of the carbonyl as well as the carbon oxygen, we can confirm there is a presence of ester group. Now, there is a value here 2984, that is a carbon hydrogen stretch of alkyl group. That may be the CH3, CH2 or CH. Now, come to the your next spectra, that is NMR. Now, what NMR says, there is a presence of, again, you have to calculate the number of protons from the integral height. If you add together, you can see this is 15 millimeter, this is 15 millimeter, and this is maybe the 10 millimeter. You can see that easily this height and this height is different. Okay, so this 3 proton, this 3 proton, and this again 2 proton. And there is a triplet quartet pattern that confirms there is a presence of ethyl group, and there is a presence of this particular methyl group, because it belongs to the 3 proton. Now, if you see the proton decoupled spectrum, we will have here 1, 2, 3. That is CH3, CH2, CH3 peaks, and there is a carbonyl stretching frequency 2. Carbonyl del value 2. So this carbonyl value is missing here in BPT. That means this is a quaternary carbon. Here this is the CH2 because it is a negative peak, and these are the 2 methyl groups. So from this structure, we come to know there is a presence of CH3 group attached to the CH2, that means ethyl group. There is a methyl group, and there is a ester. So from this, you can easily confirm that there is a presence of CH2, CH3, CH2, C double bond, O, CH3. Now, whether it is a methyl acetate or whether it is a ethyl acetate, because if you see here, this CH3 group are having 2 point something value. That 2 point something value means this CH3 is attached to the carbonyl group. That means this should be CH3 C double bond O. Okay, so that means this structure will be ethyl acetate, because this CH2 having 4 point del, that indicates this CH2 attached to the O. So if this is attached to the O, that means the ethyl group attached to the O of the ester. So from this data, you can easily confirm this structure belongs to ethyl acetate. From the mass spectrum, we can easily work out, as the values are given. There is a 29 that ethyl group easily go off as a fragment. There is a 43, that means acetyl group, and this M plus is 88. So from this data, it is very much clear to you how to take the structure out from this given data as a spectrum. Let's move on to the couple of more examples. Something unique I will take now. Okay, this is 4. Okay, now just take the similar structure, because if you see the structure 3, which is also having a molecular formula same, the C4H8O2, and now this is also having the 1744. That means this is also ester, but the values are a little bit different over here. Here M plus is also same. That means molecular ion peak will be same, but fragments will be different. Now, what fragments will be different? Now you can see here from the proton NMR, there is a triplet quartet, that means ethyl group is there, but the methyl group, which in the earlier case was something like 2 point something value, over here this is 3.4 or 3.5 value. That indicates this CH3 group now here is attached to the oxygen, and the CH2 is joined to the carbonyl group, because this value is 2 point something. That means this is an isomer of that ethyl acetate. So the structure will be exactly opposite that. By changing the position of the ethyl group will be attached to the carbonyl group now, and methyl group will be attached to the oxygen. So the structure will be methyl propionate. and the rest of the thing will be exactly same. So this way, the isomer structures of the ethyl acetate and the methyl propionic will be looks. Move on to the next structure, structure 5. Now this is something halide. Halide, if you see the molecular formula, you can easily work out that there is a that halide, or whether there is a something like olefinic compound is present or not. That easily can be worked out again by taking out the degree of unsaturation, where in case of halide type of thing, you have to add two numbers of hydrogen in hydrogen number. That means the carbon will be 3, hydrogen will be 6 now, because two hydrogens are there. So at the place, sorry, two halogens, that means two bromide. At the place of two bromide, you are going to add two hydrogen in the number of hydrogen. So it will be 6. 6 means 3 minus 3. So the degree of unsaturation will be 0. So if you see here in the UV spectrum, there is no significant peak, but still you have to comment that there is a presence of halide. That means there is a lone pair of electron, sigma bonds are there, and the prominent transitions are possible in case of the halide is N to sigma star. So this N to sigma star transitions are possible around 200. So that you have to comment. Sigma to sigma star, which is a vacuum area, there is far UV radiations will be used. So normally we don't study sigma to sigma star, but N to sigma stars are possible in case of halides and alcohol. From the mass spectrum, it is very much clear the two peaks which are having the same intensity, because the proportion of this bromide in the nature is 50% roughly. So that's why the height of this is different. Now here there are 3 peaks given, like 86. There is a molecular ion peak M plus 2 plus M plus 2, because there are 2 bromides. So there will be twice 2 plus will be added. That's why 86, 88, and 90 will be the M plus value. So this is about the mass spectrum. IR will not have any prominent peak, because there will be only carbon bromide stretch, and which will be in the range of something like maybe carbon stretch or carbon halide. So it will be 500, 600, 700 in that range. So that will again not prominent, but there is a possibility to have carbon hydrogen stretch of alkyl group. So that will be in the range of below 3000, so 2970. And there is a carbon stretch, obviously that will be in this particular area. Okay. So you have to comment, like, you know that this is a the halide structure, and that halide structure may have the carbon stretch, or carbon hydrogen stretch, and carbon bromide stretch. So you have to comment on that particular value. More to the proton NMR, there is a single peak, and that single peak belongs to the symmetry of the molecule. If the molecule having symmetry, that means the two proton, like take the example of proton coupled C13 NMR spectrum, there is a triplet. So the triplet indicates that there is a presence of CH2. So that CH2 will be twice. So the 2 CH2, they are similar. That means this molecule have exact symmetry in between the CH2. So the 2 bromide, the 2 Br will be attached to the each CH2. So if you see the structure from this, it's very simple, that CH2 attached to the CH2, and this CH2 attached to the Br one end, another end Br. So this structure will be 1,2 dibromoethane, and that which is easily confirmed by means of this mass spectrum if you just look into the fragmentation. So if you see the next one, something different type of spectrum we'll see. Sixth one, if you see here, in the UV spectrum, something different informations have been given. Now here, they have given lambda max, that is 289, and epsilon value is log to the base 10, epsilon is 1.4. If this number is 3.7 or up to 4 point something, that then there is an extended conjugation. If this value is 1, 2, 3, then there is no possibility to have the extended conjugation. So this possibility is pi to n to pi star transition for 289. So obviously through the degree of unsaturation, you will come to know how many double bonds are present. So 4 means 5, take the half of the carbon, hydrogen, so this will be 3. So 5 minus 3, so there will be a 2 degree of unsaturation. That means there may be the double bond present in this molecule. So the carbonyl peak is already over there, 17, 16. So carbonyl group is there. Okay. So if the carbonyl group is there, and if you say there is another double bond, that may be the carbonyl group or maybe the twice carbonyl group. Okay, so the carbonyl group or olefinic group. It is possible to check over here in C13 NMR. Now, if you say there are 2 degrees of unsaturation, one is with the carbonyl group, another maybe your olefinic. So if you see the proton NMR, there is no value around 4 to 5 or 6 in this particular region. That means there is no olefinic carbon or olefinic hydrogen. That confirm there is a presence of maybe 2 times carbonyl group. So 2 times carbonyl group gives something different informations. Okay, let's let me get back to the actual spectrum, which is 6 number, I suppose. So 2 carbonyl group may be the possibility. As I told you, from the degree of unsaturation, most of the cases, what we do come to know whether there is a possibility to have the carbonyl group or olefinic double bond. So the olefinic double bond condition is ruled out because the proton NMR does not belong any peak in that particular chemical shift, maybe 4, 5, 6. So it is transferred over there. So that means there is a possibility to have the 2 carbonyl groups. So the carbonyl group 1760 is what mentioned here. There is a aliphatic CH trace, no doubt. Always mention aliphatic CH trace that will be below 3000, that is 2970, 2980, 2950, so and so value. Okay, so move on to the next. That 43 is the acyl group peak. Yesterday we have discussed. So there is a presence of acyl group, no doubt, in this structure. Look at here, C13, there is again single peak. If you see the proton coupled, okay, proton decoupled spectrum, that is obviously the single line, that is one peak around alkyl range and another one is the carbonyl. Okay, so it is close to the 200. That means there is a possibility to have the ketonic carbonyl, and the DPT says there is no CH2 present in this molecule. So what else present? Now from this 3MR, it indicates there is a presence of symmetry, that twice molecular part is repeat and which is exactly same. So if having 6 hydrogen and there is no presence of CH2, that means there are twice CH3 which are equivalent. Twice CH3 which are equivalent, that means it should have that CH3 twice, and there are 2 carbonyl group. If you see match this, that CH3 C double bond O, like CH3 C double bond O, C double bond O, CH3. This is the possibility by looking at the molecular formula. And if you see the fragmentation, 43 is the prominent peak in the mass spectrum, and which confirm that this molecule may be the 2,3 dione, propane dione, sorry, butane dione. That means diketone. That is 2,3 butane dione. That means the structure will be, which is confirmed from the data given, that this is a CH3 having C double bond O, again the C double bond O, and the CH3. So this structure confirmed because there is a absolute symmetry, and that's why in proton NMR you will have only one peak. So this is the confirmation. Now, if you see the spectra number 7, again you will see that there is a symmetry, single peak. That means this molecule will also have the symmetry, but this time this CH, that carbon proton thing, that is this proton peak, belongs to the only one group of proton, that is having again symmetry. But if you see the DPT, there is a negative peak. That means this particular compound will have a CH2 now this time, and there is a one DPT peak around 120. That indicates there may be the highly electronegative carbon, maybe the aromatic, which is ruled out because there is no presence of the 6 carbon. So Another possibility, we can see that in the CM, in the IR, there is a value around 2249. This indicates the triple bond state, which may be the acetylenic triple bond, or it may be the carbon-carbon triple bond, or carbon-nitrogen triple bond. So there is a presence of nitrogen over in the molecular formula. That means the twice CN groups are present in this molecule. So if it is the case, there is an absolute symmetry in the PMR. That means this compound will be the 1,2 dinitrile compound. So this is a 1,2 dicyano compound. That is, if you see in the IPAC format, so it will be the 1,2 butane nitrile, that is CN attached to the CH2, CH2, CN. So this is what 1,2 dicyanoethane, you can say like that. So having absolute symmetry, and that structure can be like this. So this CH2 and CH2 will be this peak, and this attached to the CN to end, to this end, and to this end CN. So this will be the absolute structure, which is confirmed by PMR as well as C13. Okay. And no doubt the mass is the confirmations which we can easily work out. Look at the structure 8. Now the structure 8 have something unique thing again. Most of the time I'm taking the example having the complete symmetry. Now if you see the proton NMR, there is only one peak. That means this structure again have the absolute symmetry. If this absolute symmetry is there, go back to the UV again. It must have no prominent peak, but still we have to work out whether any double bond is there or not. So this time carbon is 8 and H is 19. If you take the difference of this, obviously there will be no double bond. So this is completely the hydrocarbon. It contains only the carbon and hydrogen. That's why this is a hydrocarbon. No functional group present at all. So if you see here IR, there is a peaks of alkyl group, only that, maybe the CH3, CH2 and carbon hydrogen stretch. Other peaks are not that prominent. There is a carbon-carbon stretch, obviously, carbon, hydrogen and carbon-carbon. If you see here, C13 spectrum again, C13 proton decoupled will have two peaks. Over here, this is a 1, I will highlight this. This is 1 and another one is this. Now this belongs to something quaternary carbon, and this will be, because this does not reflect over here. In DPT it is missing. That means this is a quaternary carbon, and this is must be CH3. So all the CH3s are present, and the molecular structure is C8H18. So how to solve such type of structure? Now if you see here, carbon having 3 CH3 group, carbon having 3 CH3. So this is a quaternary carbon attached to the another carbon, and this is also having 3 CH3. If you see here, 3 CH3 means 9 proton to this side, 9 proton to this side. So this will be 18 proton and 4 proton carbon to this side and 4 carbon to this side. So that means this structure is absolutely the 2, 2, 3 propane. That means the structure will look like this. If you can see here, I will just draw quickly. Carbon is having 3 CH3s. Okay, this one, and this one. And this carbon attached to the another carbon having the similar CH3, 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 and CH3. So this means this is the absolute symmetry in these molecules, and this can be easily confirmed by use of the proton as well as C13 as well as, no doubt, absolutely mass will be the correct information about this structure. Look at the 9th structure. 9th structure is something having similar thing, more symmetry, but there are 2 peaks, and here there is a D2O exchange. Now this OH belongs to maybe the active proton. Now this value is roughly in the range of 3, so it must be a OH peak, which will be confirmed by IR, because in the IR 3458, that is the peak of OH stretch, so which is confirmed. Then again we have the carbon hydrogen stretch. Now again we don't have any prominent peak. Look at the degree of unsaturation, 7 minus 7, so it will be a 0 degree of unsaturation. So there is no any pi to pi star transition, but there is a possibility of N to sigma star transitions because this is alcohol. Now, if you see here, again back to the proton, so there is a presence of OH, but there is absolute symmetry. So this integral height you can easily work out what exactly the peak. Now, if you see, this is from the DPT, there is a presence of only CS3 and there is no presence of any CH2. That means there is again the quaternary carbon present, because the quaternary peak is around over here. This is your quaternary carbon, which is not missing, which is missing in DPT. So the structure would be like this carbon is having two CH3s having one OH, and this is absolutely the same to other side. So this is the alcohol, which is 1, 2, 3 diol, 2, 3 methyl having a substituent. So this compound, if I would say, the structure will be this carbon having 2 OH over here, and rest of the thing will be with the carbon. So this 2 plus 2, 4 carbons having the absolute symmetry because of the molecule having symmetry in it. So this is how to solve such types of problems. Now you can easily work out this type of things, but in the examination, how to write down this, that I will show you now. So just give me a minute. I'll share the PPT once again. Now, is the PPT visible to you? Okay.
Yes, sir.
Now look at here. This is the problem. How to read the spectra. Now I have taken this example. Now, if you see the example, you have to first look into the molecular formula. So this is the molecular formula C9. Okay, C9H11NO2. Now, first of all, calculate the degree of unsaturation. So that will be the first thing. And then comment on each spectrum, what exactly the present. Now, this is a bit complex spectrum I have taken for this study. Now, there are no doubt the complex spectrum, but once you understand the idea about the spectrum, how to read, it will be easy to comment on the spectrum. Now, how to comment? Now, look at here, the IR or UV. UV is very simple. As I told you, epsilon value you have to calculate from the data given, that is the concentration given. Then again you have optical density mentioned over there. IR, the values will be mentioned over there. Then C13 also you have the values mentioned. Proton NMR also values are mentioned. But how to write that? So if you see here, that from the structure, what you got, the molecular formula is this. The molecular compound, how the molecular weight is 165. You can easily work out. So this is a molecular ion peak 165. So this is a molecular ion peak. So the molecular weight is 165, that in your comment. So second one, from the molecular formula, you have calculate the degree of unsaturation. Now here, some another formula, that means the same formula, we have taken X minus Y. In y place we have taken N and M. So same formula, and they can have calculated degree of unsaturation. So this is another thing which is you have to prominently read it out from the spectrum. C thing, they are commented from the they have taken out the data from the proton NMR. What values are present? Now whatever values are there, now straight away take this roller and put across the scale, and this peak having 1 point something triplet. How many protons? Now 2 proton, 3 proton. How to calculate that? That also I have shown you integral height. Take the integral height all together and add together, and you will you have to divide with the hydrogen number and you will get the number. So millimeter height, if you calculate, it's okay. If not, that also okay. Because sometimes you may come to know that triplet, quartet, doublet pattern, if it is there, from that you can easily work out that this is a CH3 and this is a CH2, because this is a triplet quartet pattern. CS3 belongs to this. The CS3 will have a triplet, that means it's attached to the CH2. This quartet is, it should attach to the so quartet belongs to what? CH2, and this belongs to CS3 belongs to that ethyl group is confirmed. That is a simple the wording for this. And there is a doublet of doublet. So the doublet of doublet height also you can calculate. Doublet of doublet is always 2 proton. So this is 2 proton, this is 2 proton. Obviously, this height is a little bit more. This is a 3 proton, this is your 2 proton. So you can easily work out because this height is again with the D2, that is a proton, which peak is absolutely lying there only. If you see here, this height is a little bit more because of this OH peak. Also, there is a OH peak. So in this structure, there is a presence of hydroxyl group too, because this can OH, or it may be the NH, because nitrogen is here. It's not always OH, it may be the NH. So so you have to comment on this. So how to read out that? I have shown here. This you have to read out that these are the values here, and the integral height we have calculated, and then we have mentioned this value belongs to this many proton, and so on. So from that, again, this as I told you, 1 proton is equal to how many millimeter. That easily you can calculate it from this values. So this you have to mention. Then comment on the C13. How many peaks are there? Their values. Okay, if there is a DPT given, or off resonance spectra, or maybe the proton coupled spectra is given, then from that you can easily comment there whether there is a presence of CH3, CH2, CH, and that data will be from the C13. Now, most of the cases, while reading the spectra, the data can be provided to you. So the handbook can be used in this the process. For first half an hour, the examiner will allow you to refer the handbook, but for the analysis point of view, you need not to refer any handbook. So second one, you have to calculate now the molar extinction coefficient by taking the concentration from the UV spectrum. That also I have shown to you. So you have to write like this. So calculation of the some values of epsilon, and then comment on that whether it possesses any extended conjugation or not. And then IR stretching frequency, how many frequencies are possible. That 1680 is there, that is for carbonyl. Then there is a M plus value that is given, and that differences which group is present. And then from IR, that epsilon value is 17,000. That means there is extended conjugation. So that type of data you have to solve. You have to start solving. Now here in the first, you have read out the spectra. The data is given so and so. Now from this data, you are going to solve the problem. Now this is a problem. You consider this is a problem. Is data given from that spectrum. Now you're going to solve it. Now how to solve? Now each spectra has given certain informations, and that value related to certain thing. Now suppose if I would say this compound have carbonyl stage 1680. Now 1680 is a bit lower value because of the extended conjugation. So that's why this carbonyl stretching frequency is because of the extended conjugation, the strongly conjugated ketone. So that is the comment on solution. The another values will be from mass spectrum, and it is confirmed that there is a presence of ethylene group. So that mass spectrum shows that there is a loss of 28 units. So you can comment on that. From the UV, again, you have come across from the calculation, there is 17,000, that there is a large epsilon value. That means there is a conjugation present. So extensive conjugation is appear from the large value of the epsilon. Then come to the proton NMR. Then again you have to comment on each value. Now the del values will be given, and from that del value will come to know whether there is a presence of CH3 group, CH2 group, or maybe the methyl or the quaternary carbon from C13. So all this data you have to compile together, and you will get some structural unit. And that structural unit from all this data will be the disubstituted aromatic ring. There is a presence of ethoxy group. There is a presence of carbonyl group. So this type of structural units are present from this data. There is a presence of NH2 group from the data. So if you analyze the complete structure, what probable structural units you come across, that there is a disubstituted aromatic ring, there is a ethoxy group, there is a carbonyl group, there is a amino group, that NH2 group. So if you assemble all these groups together, so you have a probable structure. So this is a probable structure. maybe the this type of aniline derivative, or this is ethyl benzoate derivative. Okay, or it may be the amide. Okay, so these are the A or B structure. These two possible structures are there. So these two possible structure, whether they are matching to the spectra which are given to us, that you have to justify now. Now justification is that if you see here, there is a presence of NH2 group, and that is exchangeable with D2O. The data is provided here. You see here that this is exchange with the D2O. If there is exchange with the D2O, that means there should be a free NH2 group or OH group. The NH2 group have the ability to give the proton with the impurity, and or amide particularly is strongly bounded because of the carbonyl is electron withdrawing group. So this is always in the conjugation. So it is not possible to remove the H with the deuterium. So the deuterium exchange is not possible with the amide. So this is ruled out that this structure cannot be possible. But there is a possibility to have this aniline derivative. So which will be confirming with the another data too, where there is ethoxy group present, and the del values are 4.37 and this 1.38, which is completely matching to the data given over here. Because there are the two values again, whether this is as a ether or whether it is a ester type of thing. Okay, so ether and ester will have different values, so that also you have to compare. This is a possibility, because this is going to be ether and this is going to be a ester. So one thing we have ruled out, there is no possibility of amide, so need not to think about the ether. But still, for extra things, you have to comment like this. If we have a knowledge, it's not compulsory to comment on that. Now from C13, what data we have taken, that you have to match again, and then you have to confirm the structure by mass spectrometry. Now suppose we come across there is a presence of aniline derivative. So this ester group is there, and there is a possibility to have a Mac-Lafferty rearrangement because there is a presence of gamma proton, and this Mac-Lafferty rearrangement loses the ethylene group. Actually, in the analysis case over here, we have confirmed that there is a presence of ethylene, that is loss of 28 group, and we have confirmed there is a presence of ethylene. That is a probability. It may be the ethylene or it may be the carbonyl group, because these are the 28 units, but which is confirmed by the mass spectrum. There is a loss of ethylene because of the Mac-Lafferty rearrangement, and that Mac-Lafferty rearrangement confirms there is a loss of ethylene group, and that loss of ethylene will give you the unit which we have mentioned over here, 137. Another things are also possible, another fragmentations are also possible, and they will give the exact number which is given in the mass spectrum. And from this data, you can easily confirm that this structure is what we have analyzed in the mass spectrum, and that structure will be 4-amino. This is ethyl 4-amino benzoate. So this is the correct structure. And the other one, that is the amide, benzamide derivative, is not the correct structure because it does not show the D2O exchange and the other stretching as well as stretching frequency, as well as the chemical shift values which are given to you. So whenever you solve the spectrums, any spectrum, you have to first write down the values from the spectrum. Then you have to analyze that value, and then you will get a structural unit, and then the structural unit will have to assemble together to have a probable structure, and that probable structure you have to confirm by a mass spectrum by drawing the fragmentation, and that is what the confirmations. And it is expected in the examination that you need to draw the mass fragmentation at the end, and that carries maximum marks. So this way, sometimes you may get very easily structured, like just looking at the spectrum. You will come to know, okay, this is the structure, but just writing down the structure in the examination will not sufficient. You will not get absolute marks. You have to analyze each and every aspects or spectrum given, and that analysis at the end, confirmation by mass spectrum will carry the marks, absolute marks. Otherwise, just knowing the structure from the spectrum and drawing spectrum, and that is the enough thing, will not be appreciated in the examination. So you have to write everything, and then you have to comment on each value. That is called a justification and confirmations by the mass spectrum. Now this is about how to draw the structure. Now tomorrow's lecture we are going to see some of the structures or the spectrum without any molecular formula. So the molecular formula will not be given. Elemental analysis will be given. From the elemental analysis, how to draw the molecular formula, and then without molecular formula, how we will justify the structure of the unknown organic molecule. That type of things tomorrow we are going to discuss, and we will see some of the complex structure. Today we are discussing some simple spectra, but tomorrow we will see some complex structure and their analysis too. So today I'm going to share this presentation with you. You just go through it, and if you have any doubt, you can comment on the WhatsApp group as well. Okay, so thank you very much. We'll stop here.